So this is going to be a solution video for the linear versus angular acceleration homework that we had. And when you went through this homework, you probably noticed something really important, and that's that the way that angular acceleration and angular velocity are related, and the way that linear velocity and linear acceleration are related are the same. Okay, and that's summarized in these equations that I have right here. And so when we're going through this, we're going to see that really the way that we do the calculations is essentially the same. So let's first start with the first problem. So this one says, consider a particle constrained to move in one dimension with a linear acceleration given by a of t is equal to a1 t cubed. The particle begins with initial velocity of v0 at the origin. We want to first find the velocity as a function of time for this particle. So what we're going to do for 1a is we're going to say that a of t is equal to dv dt, which is going to be equal to a1 t cubed. And we want to find this v here. And so in order to do that, we say we're going to multiply both sides by dt. So we have dt, dv, dt, a1 t cubed. And then we're going to integrate both sides. And so when we do that, we're going to end up having v of t is going to be equal to the integral of, I'm missing my integral sign in my dt here, but this is going to be a1 t cubed dt, which is going to be equal to a1 t to the fourth over 4 plus some constant integration. Now to find the constant integration, what we do is we say we know actually that when t is equal to 0, we have some initial velocity of v0. And so then we evaluate this function here. We say this is going to be 0 to the fourth over 4 plus c. This right here is itself 0. And so this says that c is equal to v0. And so our velocity as a function of time, our v of t, is going to be equal to a1 t to the fourth over 4 plus v0. Okay, that's the answer to part 1. So the next part, we want to find what the position as a function of time is. And we have the equation for that. This is, 1b. So for 1b, we have that the position as a function of time is related to the velocity as a function of time, according to v of t is equal to dx dt. Let's get rid of this notification real quick. V of t is equal to dx dt. And so then we can say that we're doing the same thing that we did in the last part, because we want to integrate this ultimately. So we multiply both sides by dt, and we integrate. So this says that x of t is equal to the integral of a1 t to the fourth over 4 dt plus the integral v0 dt. Okay, so this is going to be a1 t to the fifth divided by 20 plus v0t plus a new constant integration. And so we have x of t is equal to this. To find this new constant integration, we say that we know something about the position at time t is equal to 0. And so we're going to say this is going to be equal to 0, which is 0. So this is a1 0 0 to the fifth divided by 20 plus v0 0 plus c. So this c is equal to 0. And so our position as a function of time, x of t, is going to be equal to just a1 t to the fifth over 20 plus 0. So it's just a1 t to the fifth divided by 20. Okay, so that's our position as a function of time. And then for 1c, we want to find what the units of a1 are. And so if we go all the way back to our original equation, we had the acceleration a of t is going to be equal to a1 t cubed. And so then we know that the units of the acceleration are units of meters per second squared, and the units of t cubed are units of seconds cubed. And so in order for this to work out, that tells us that the units of a1 are going to be seconds to the fifth, right? Something's wrong. Something's wrong. Great. This is going to be meters per second to the fifth. There we go. There we go. And you can see that, even when I make a mistake and I write something down, I'm thinking about it, and I'm like, okay, well, is the thing that I just said true? And sometimes what ends up happening when you do that is you think about it two different ways, and you say, okay, is the way that I thought about the first time the same as the second time? And if they're not, one of them is probably wrong, and you have to kind of reconcile the two. And that's actually what I kind of did quickly in my head. I am a little crazy. Okay, so moving on to the next one. We got 2a. We have this, instead of having this particle that's translating according to some acceleration as a function of time that's a linear acceleration, we have a angle given as a function of time. So this is going to be something that's going to go around the arc of a circle, and the angle as a function of time is given here. Okay. So we have theta of t is equal to a2 t to the fourth. We want to find what the angular velocity is as a function of time. So in order to do that, what we're going to do, so this is going to be 2a. So theta as a function of time is going to be equal to, this was a given by a sub 2 times t to the fourth, I believe. Let me just check that really quickly. Yep. And we want to find the angle as a function of time. So what we want to find the velocity as a function, angular velocity as a function of time. So we have this relationship between the angle and the angular velocity such that omega of t is going to be equal to d theta dt. And so what we're going to do is we're just going to take a time derivative of theta of t, which is d by dt of a to t to the fourth. And this is going to be equal to 4a2 t cubed. So that's our omega as a function of time. Next thing what we can do is we can find the angular acceleration as a function of time. This is just going to say that alpha, the angular acceleration as a function of time, is going to be equal to d omega dt, which is going to be d by dt of omega of t. This is equal to d by dt of 4a2 t cubed. So this is going to be equal to 12a2 t squared. So that's alpha of t, and I don't quite remember what the next question is asking. We want to find what the linear velocity in the theta direction is v sub theta of t. And so we have this relationship between the linear velocity tangent to the circle and the angular velocity. And this says that, for 2c, that v sub theta is going to be equal to r times omega. And so we can just take the omega that we have here. So take this omega that we have here, and we plug it in here with our radius. So this is going to be 4a2rt cubed. Okay. So something you might have noticed that I did when I went from here to here is I kind of put this in a standard format that you might even notice in textbooks that when you're going through here. So when you're writing these things out, typically the way that you do it is you put the number first, you put the variable for the function last, and then everything else is in between in some order that it's hard for me to say offhand exactly what that order is, but that's a very standard way to do this, as opposed to, because algebraically it's true that you could have written this as t cubed 4a2r. Those are the same thing because you can interchange the order that you're writing these things in. But something that you guys will pick up, and I picked up over time, was this kind of standard notation for the way that you're representing these things. Okay, so the next thing that we have here is we want to find how long does it take for the particle to attain an angular velocity of omega 1. And so what we're going to do is we're going to go to our angular velocity equation. So this is going to be 2d. So we said our angular velocity as a function of time is going to be equal to 4a2t cubed. And we want to know how long does it take for this to have an angular velocity of omega 1. So what we can do is we can say omega 1, that angular velocity, is going to be this function omega of t evaluated at a very specific time. And the way that I've been doing this is I'm saying the special time that we're looking for is the t star. And so this is going to be 4a t star cubed. And then we're going to take this equation that I have here and then just solve it for t star. And so when we do that, what we end up having is omega 1 divided by 4a2, and then we have t star is going to be equal to that, and then this is going to be to the 1/3 power. Okay. Now, the last thing that we want is what is the angle that this is rotated through when this has an angular velocity of omega 1. Okay. So in order to do that, so to E, we say that theta 1, we can say that that's the specific angle that we're looking for, is the function theta of t evaluated at this special time, and theta of t was given by a1 t to the 4th, but really we're evaluating this at t star, so this is t star to the 4th, and so this is going to be a1 times omega 1 over 4a2. Sorry, my indices aren't right here, so this is this should be an a2, because a1 was actually from the first problem. It's not related to this at all. So then this is going to be this to the 4th power, so this is 4/3. And if you'd like, you could simplify this a little bit. And that's the answer to that one. Okay, so that's going to be it for this video. So here we saw the way that we work with linear velocity and linear acceleration is really exactly the same as the way that we work with angular velocity and angular acceleration. All right, take it easy, guys.